Now I show you a coil of insulated wire connected to a galvanometer. When one end of a bar magnet is pushed into the coil, the galvanometer deflects. This is because the movement of a bar magnet causes an induced EMF in the coil. The induced PD causes a current because the coil is part of a complete circuit. If the bar magnet is then withdrawn from the coil, the deflection in the galvanometer shows in the opposite direction. This means current is set up in the opposite direction. The deflection of the induced current also depends on which way around the polarity the magnet is.
A coil in a magnetic field can be forced to turn by passing a current through it. This video shows a rectangular coil between the poles of a U-shaped magnet. When a current passes around the coil, a force acts as shown on each of the two long sides of the coil. As these forces are in opposite direction, they act to make the coil turn. If the coil is made to rotate continuously, electrical energy is converted into mechanical energy. Such an arrangement is called an electric motor.
In a practical electric motor, the rotating part of the motor or the armature consists of several evenly spaced coils wound on an iron core as shown in this figure. The iron core makes the field much stronger, so the turning effect is much greater. Each coil is connected to its own section of the commutator. The result is that each coil in sequence experiences a turning effect when it is connected to the voltage supply, so the armature is repeatedly pushed around. Because the iron core makes the field radial, as shown in this picture, each coil is in the field for most of the time. As a result, the overall turning effect is much steadier than in a simple electric motor, with one coil only, so the motor runs more smoothly.
An electric motor is designed to use the motor effect. The simple motor in the picture consists of a rectangular coil of insulated wire that is forced to rotate. The coil is connected via two metal or graphite brushes to the battery. The brushes press onto a metal split ring commutator fixed to the coil. When a current is passed through the coil spins because a force acts on each side of the coil due to the motor effect. The force on one side is in the opposite direction to the force on the other side. The split ring commutator reverses the current around the coil every half turn of the coil. Because the sides also swap over each half turn, the coil is pushed in the same direction every half turn.